Hello everyone, my name is Amir Tabatkani and I am a second-year PhD candidate at Deakin University in Australia. This presentation is mainly about my research proposal and undergoing discussions. As we all know, shading systems are necessary to control solar gain or daylight that both can affect users' thermal and visual performance. On the other hand, user comfort conditions might vary from a single space to a shared space. In a shared space, individual control, ownership, and responsibility are more challenging comparing to a single space where comfort contradictions occur for only a user. Therefore, to overcome these challenges at design stage, individual users should be the unit of analysis rather than a group of users. So if I want to personalize an adaptive facade, what type of facade is the most suitable one for my investigation? Adaptive facades can be classified into two groups based on their motion layout. On the left, we have the simple motion layout as conventional adaptive facades like Venetian blinds, and on the right, we have the complex motion layout as non-conventional adaptive facades that contains three different design approaches. First, using translational or rotational movements. Second, using folding techniques. Or third, taking the advantage of nature principles towards biomimetic skins. In general, conventional adaptive facades are characterized by shared elements in which their flexibility is quite limited, while non-conventional adaptive facades have higher adaptation flexibility that allows finer resolution control over each part of the facade. In practice, there are two main control strategies: automatic and occupant-centric shading controls. After conducting two different critical analyses for 66 studies, the top 5 knowledge gaps are outlined here. As the main finding, there is no control method in a shared working space that allows individual users to adjust the shading system based on their demands and desires. Therefore, with respect to automatic shading controls, we have the open loop that there is no feedback loop. We have the closed loop that allows feedback loop but treats all occupants as a homogeneous group. While with respect to occupant-centric controls, we have the manual control, which compromises energy savings, and there is no framework in a shared space. We have the user-oriented control, which is individualized, but not for a shared space. And finally, we have the predictive controls that require a learning process and direct user interactions are limited. So I introduced a new system called personalized real-time control with a specific definition as I stated that the aim is synchronizing users' feedback in the loop to control part of the adaptive elements. Therefore, to achieve the research aim, two main questions are going to be answered during my PhD research. Regarding the first question, I would like to outline the benefits and limitations of non-conventional adaptive facades to the conventional ones through the implementation of a PRC system. The second question is in response to several potential concerns in a shared space, such as who should control the shading system, or do I disturb my colleague if I close the shades? So my research methodology includes two main sections. Section 1 is about choosing a hypothetical case study. This case study has been co-developed by myself prior to my PhD candidature and is documented as a patent in 2018. The prototype is inspired from an origami technique that enables the possibility of personalizing its modular structures. And from modeling perspective, indoor space is divided into 7 zones, including 6 individual target zones for 6 users and 1 zone in depth. Section 2 refers to the research methodology, which is based on an integrated simulation workflow that takes into account the existing interactions among these interfaces. Grasshopper is used to model complex and non-planar geometries. Ladybug tools are employed to deliver essential calculations and files to DaySim. DaySim is used to run daylighting and glare simulations. Python is used to script the control algorithm based on the pre-calculated simulation results. And finally, EnergyPlus will be used to calculate the annual energy and lighting loads. However, since the number of shading positions and time intervals result in a large number of simulation iterations, it would be a time-consuming approach if we increase the resolution. Therefore, I assumed a case study that is divided into 3 columns that each one can be controlled individually based on user preferences. And to select the most feasible workflow, I decided to break down the entire iterations by employing 10 cloud-based machines with high configurations. The concept of the PRC system includes 2 main scenarios for an air-conditioned shared space. Scenario 1 is the energy mode adaptation when occupants are not present in the office, in which an automatic shading control in response to incident solar radiation on a window will take place to reduce the cooling loads. Scenario 2 is the visual comfort mode adaptation in occupied hours, in which each user might have a different time schedule for their presence in the office. In this scenario, two different actions are considered. First is when a user decides to adjust the shading system as an active user due to visual discomfort, in which a time-dependent prioritization will take place to satisfy the user's request in timely manner. Second is when user does not take any actions as passive user, in which an automatic shading control based on task illuminance will take place to save the lighting load. Since no surveys or experiments will be conducted during my research, user preferences will be assumed as pre-calculated simulations, but in reality, these observations can be delivered from user interfaces such as smartwatches. And final energy calculations are based on a new simplification method called shade factor as transmittance schedules. With respect to control aims of this research, on the left we can see the variations of task illuminance for each user, while on the right results are showing the glare index. It is good to mention that unlike a centralized mechanism, a decentralized mechanism has a significant impact on individuals' comfort condition that has the potential to create localized comfort condition in a shared space. As another part of the comfort indication that might be influenced by shading adjustments, here are the results for the variation of occlusion rate to choose the optimum shading position with respect to view connection to outdoors. Also, I would like to outline two of the main contributions of my research. The proposed control algorithm can empower the implementation of user interfaces such as new open source smartwatches, and to adjust the shading system in 3 steps: synchronizing the input signals, prioritizing the feedback among users, and finally optimizing the shading modules within a decentralized mechanism. Also, the proposed control algorithm provides an essential step towards assessing the performance of non-conventional adaptive facades during design stages, where there are no occupants to run surveys or no building and experiments to test the prototype. However, there are other aspects that need to be taken into consideration, such as additional costs, structural issues, or life cycle assessment that are not the aim of this research.